Hi everyone, thanks for checking out this video. Also, I'm sorry about there being a bit of a glare on the board. This is actually my first time filming a video in my new apartment, so I'm still trying to figure out kind of the filming and the lighting situation. But yeah, for today there's a bit of a glare, so I apologize about that. Hope you guys can still see okay. But yeah, so this is going to be a video about how to simulate the Lotka-Volterra Predator-Prey model using Euler's method for numerical ODE solutions. So this is actually like the third video I'm making in this short series on numerical methods in Python. So if you guys haven't already seen it, I recommend like checking out my first two videos where I kind of explain the basics of Euler's method. But yeah, so this is the third video I'm making in this series, so this will be like a little bit more practice with Euler's method, and this time I'll be using the Predator-Prey model for an example. Yeah, so I'll just start by giving like a quick review of the model. So we have two equations. One of them is modeling the prey population, and then one of them is modeling the predator population. So I just called the prey X and the predator Y. And then for the prey population, we have some growth term here where we have a constant parameter A. It's like the growth rate of the prey population. We have the growth term here, a times x, and then minus another constant parameter b times x times y. So this here is the death term for the prey, and you can see that the death term for the prey depends on the current level of the predator population, y. So y is, remember, our predator population. So the more predators there are, the higher the death rate is for the prey, basically. And then for our predator equation, dy dt, we have some growth term here with a constant parameter c. So this is the growth term for the predator population. And notice that the growth of the predator population depends on the level of the prey population, x. So basically, the predators need to be getting enough to eat. So there needs to be enough of the prey that the predators can be eating them and then having their population grow. That's why we have an x in this predator growth term here. And then lastly, we have our death term for the predators, a constant parameter h times y. And the reason I'm using h here is just, I mean, it seems like it would go like a, b, c, d. But I didn't want to confuse people because there's a d in the differential equations, dx, dt, dy, dt. So basically here, just instead of using d, I used h for the constant parameter. But yeah, these four, a, b, c, and h are just constant parameters for the model. Okay, so let's talk a little bit about how we're going to use Euler's method to get a numerical solution to this system. Okay, so the first thing I did, just as like a stylistic thing, without really changing anything, is I just wrote, instead of dx dt, I wrote delta x delta t, and instead of dy dt, I wrote delta y delta t. So this is just to get us into the thought process of having time intervals we're dealing with, rather than the like infinitesimal changes in the variables and time. We're going to start talking about, for a numerical solution, we're going to talk about like time intervals and the ways that those variables are changing for each time interval. So I just wrote as a stylistic thing like delta x, delta t, delta y, delta t, just to get us thinking about like these time intervals. So basically, the way we're going to do our actual solution in code, when we get to the Python code, is we're going to like keep track of the time and keep track of the variables. So we're going to have basically lists keeping track of all these things. So we're going to have a list for x, a list for y, and a list for t. And then we'll have some time interval, maybe like for this example on the board, I'll just make it like 0.5. We'll just keep track of, we'll keep track of the changes in the time by just, for each iteration, we'll just add on this time interval, and then we'll calculate how the variables are changing. So maybe this will start at 10 and go to 9 and then 8. I'm just making up some numbers here for an example. And maybe this will start at like 1 and go to 2 and 3. So basically, we're just keeping track of the changes in time. with this like time interval, which I made 0.5 for this example on the board. And then while time is changing, we need to calculate how these variables are changing with each time step. Okay, so how do we do that? So it's actually pretty easy. The Euler's method is like the easiest possible numerical ODE solver. It's basically just doing it kind of the obvious seeming way. So all we're really going to do is to get the change in the variables at each time step, we're basically just going to rewrite these equations, bringing the delta t over to this side. I'm going to multiply all of that by delta t, and then erase it here. So then we basically have delta x equals the equation times delta t. And then same thing down here, just going to bring the delta t over. Oops. Yeah, same thing. Delta y equals this term here times delta t. And then the way we're going to fill up this table is it's basically going to be like the next x, which I'll call x at index I plus 1, equals x at index I plus delta x. So basically x at the next time point equals x at the current time point plus whatever the change in x is. Remember, delta x is just the change in x for this time step. And yeah, same thing with y. So it's basically like y at index I plus 1 equals y at index I plus delta y. And then t at index I plus 1 equals t at index I plus delta t. And we'll be choosing the delta t for our model, so we won't have to actually calculate that. That'll just be chosen. But yeah, so this is basically the Euler's method solution for this ODE system. We're just calculating for each time step. We're just using these equations here to calculate what the changes in the variables will be for each time step. Okay, so I hope you guys are following me so far, but if anything's confusing at this point, I think it'll even be easier to understand when we start actually writing the code, because then you guys can actually see how it'll be working like step by step. But yeah, so let's get into the actual Python code now. Okay, so I think you guys may actually be like pleasantly surprised how easy it is to write the code for this. It's actually like super easy, pretty simple, really only a few lines of code, so not that difficult. But yeah, so the first thing we're going to do is just import our usual libraries that we're going to be using. So we're going to import matplotlib.pyplot splt. This one here, we're actually not going to be using this for the Euler's method solution, but this is like the like regular like Python like SciPy ODE solver. So this is like the actual like legit ODE solver. So when we write our own like Euler's method solution, after we do that, we're going to use this to check our solution and make sure it matches like the output from like an actual ODE solver. So this will be like a sanity check we're going to use. And then numpy is np, of course. So now we're going to define some initial conditions and a endpoint for the simulation. So I'm going to say x init equals 10. This is going to be the initial condition for the level of the prey population, our variable x here. And we can think of the units here as being in like hundreds or thousands. We don't have to literally think of it as being like only 10 of the prey. But yeah, we can think of this as like 10, 100, 10,000 of whatever the prey animal is. So for this, I should maybe say before, for this like video, this isn't really like an ecology tutorial. This is like a math modeling tutorial. So I actually don't know what the like ecologically realistic parameters are to use here. So I'm kind of just making up these numbers to show you guys like the math modeling and simulation part. And then yeah, so for the predator initial condition, I'll say y init equals 1. Again, you can think of this like 100, 1000, maybe. Yeah. And then t end, the endpoint of the simulation, gonna make it 50. Again, unitless numbers here. You can think of it as maybe being like 50 weeks, 50 months. Maybe 50 years is a bit too long, but yeah, maybe like 50 weeks, 50 months. But yeah, just keeping these unitless now, just for the example. Yeah. And then so the next thing is to actually come up with some values for our constant parameters. So remember, we have 4 constant parameters. There's A, B, C, and H. I just called it H to not confuse you guys with like the like dx dt ODE notation. So yeah, I'll say A equals 1.1, B equals 0.4, C equals 0.1, and H equals 0.4. Yeah, I encourage you guys to like play around with different values for these. I'm just kind of using these for an example for now. But yeah, encourage you guys like change these around, see what happens when you change up some of these parameters. Yeah, okay. So the way we're going to keep track of all of the variables and the time points is by storing them in lists and then appending them to the list as we iterate through the simulation. So we're going to say x will be a list. We're going to start it off with only the value x in it. And then basically as we iterate through the simulation, we're going to be appending to this list to keep track of the levels of our prey population. So it's going to be appended to like, yeah, like this. We're going to be, appending values to it. Yeah. And then same thing for y. We're going to make y a list and start it off with our initial condition y in it. And then t is also going to be a list, and we're going to start it off with our initial condition t equals 0, starting at time point 0. And for the t list, we're also going to be appending to it, but we're going to be appending whatever delta t we choose. So if we choose like 0.5, it'll eventually get filled up like this: 0.5, 1, 1.5. Adding the delta t each time, basically just appending the new value to the t list. Okay, so I hope you guys are following me so far. Hope it's been like, yeah, kind of simple so far. So now we need to choose a delta t. So for now I'm just gonna make delta t equal to 0.5. Although I think you guys are going to see that when we have it be 0.5, that's not going to be exactly precise enough to match the SciPy solution. But yeah, I want you guys to see this. I want you guys to see how when we make it 0.5, that's not exactly precise enough. So I'll show you guys the solution with delta t being 0.5, and then maybe like 0.1, and then maybe like 0.01. So you guys can see how as we make the delta t smaller and smaller, we get more precise of a solution, basically. But yeah, for now, I'll just make it 0.5. Okay, so the next thing we're going to do is we're going to write a while loop to actually do our simulation. So we're going to say while t index -1 is less than t end. So the index -1 syntax here is basically saying the last element in our t list. So basically saying our most recent time point value. While this is less than t end, we're going to keep doing the simulation because that means we haven't reached the endpoint yet. So what I'm going to do next is I'm going to be a little bit lazy and just copy and paste a line of code, but then I'll explain it. So basically, within the simulation, we need to compute the next values of x and y using their current values. So this is how we're going to do that. So we're going to say the next value of x equals the current value of x plus all of this is the delta x that we wrote on the board, basically. So I know it's maybe looks a bit different typed, but if you guys realize, all of this is the delta x that we wrote on the board. It's just a times the current value of x. Again, that's what the index -1 is here. Current value of x minus b times the current value of x times the current value of y. All of that times delta t. this was the delta x value that we wrote on the board. It's basically the original equation times delta t. So I'm just going to actually maybe leave a comment about that. So yeah, next x is current x plus delta x. So you just have our current x here, and then plus, again, just, I know I'm repeating myself, but this is kind of the important part. So all of this is the delta x that we solved for on the board. Yeah, I know it looks a little bit different, but yeah, just the next x is the current value of x plus the delta x. And again, just writing exactly what we solved for on the board there. So yeah, once we have that, we're going to say our x list, we're just going to append this next x that we have. Okay, so now we have to basically just do the same thing for y. I'm just going to be a little bit lazy here, just copy and paste again. So the next y equals the current value of y index -1. That's our most recent value of y that we have. And then all of this here is the delta y. So again, I know it looks a little bit different, but this is the delta y that we solved for on the board. It's just basically the equation for dy dt, except we moved the delta t over to the other side. So it's basically this all this here, the original equation, times delta t. So I'll leave a comment here too. So I'll say next y is current y plus delta y. Okay, and then same thing. It's going to say our y list dot append next y. And then for delta t, it's a bit easier. So our next t, whoops, sorry. Next t equals the most recent value of t we have plus delta t. We don't need to calculate anything here because we're defining what the delta t is. So basically, yeah, the next time point is just the current time point plus the delta t. Yeah, and then we'll also append this to our t list. Yeah, and that's really all there is to it. That really, this is the whole simulation. It's only 6 lines in this while loop. You guys could even, you might even realize that you could have even done this a more clever way. You could have done this in half as many lines by just writing this. You could just append it like directly if you want to make it 3 lines instead of 6 lines. But yeah, I'm just writing it like this to make it as like obvious and clear to you guys as I can. But yeah, it's only 6 lines. Could have even done it 3 lines if you wanted to be more clever about it. But yeah, pretty simple simulation. Yeah, the Euler's method is really it's really like the simplest possible way of solving ODs numerically. I think it's like the most obvious way to do it. I think. Yeah, so now let's just plot some of these results. Let's just see what we get. Plot some of these results. Hopefully it'll look okay. Let's just try this out. Yeah, so looks like we got the right answer here. If you guys aren't really familiar with the predator-prey model, a lot of times you get solutions that look like this if you have the right parameters, these like oscillating solutions. So basically this blue line here is the prey population, and we start off getting more and more prey, but as we're getting more and more prey, the predators have more to eat, so the predator population is growing, and then the predator population increases. But as the predators are increasing, they're eating more and more of the prey. So the prey population then falls and decreases for a little bit. But as the prey population is decreasing, eventually the predators run out of food to eat. So the predator population also starts decreasing. But as there are less and less predators, then the prey population starts increasing again. And it goes in like a oscillating cycle like this, basically, if you have the right parameters for it. So yeah, it looks like these oscillations. But yeah, it looks like it worked okay. So what I'm going to do next actually is I'm going to check our answer against the actual SciPy ODE int solution, because this is like the actual like legit Python solver. So we're going to check and see how our Euler's method did compared to like the real like actual SciPy numerical ODE solver. So yeah, I'm just going to basically copy and paste in some code here. If you guys want to see how I'm coming up with this code, I actually have a different video showing how to do the solution using SciPy, using the SciPy method. I have a different video about that I'll link to in the description. But yeah, for now I'm just going to copy and paste in this code. Yeah, this block code here is just basically solving the system using SciPy ODE int. And then yeah, I'm basically just going to plot the solution alongside our Euler's method solution and just see how they look compared to each other. Okay, so these black dashed lines are the SciPy ODE int solutions. I just made both of them blacks, but I think you can basically tell like which one's the prey and which one's the predator just based on like where they are. But yeah, we can see that the actual solution kind of looks like our Euler's method solution, but not exactly. Like it seems like our predators are getting to a higher level than the actual like real SciPy solution. So this is what I was talking about a bit earlier, how since we used a delta t of 0.5, that's kind of a large delta t, and it's not really like that precise. But I'm going to show you guys now that as we make the delta t smaller and smaller, we get more precise solutions that kind of approach like the true solution. So now let's do another one. Like instead of delta t equals 0.5, let's make it delta t equals 0.1. So let's just try it out with like a smaller delta t and see what it looks like. Yeah, so you guys can see with the smaller delta t, it looks a bit closer to the SciPy solution. So we're getting like a bit more precise of a solution here with this smaller delta t. It's like a better it's a better numerical approximation of like the true solution, because yeah, like these numerical methods, even the SciPy one, ultimately it's like an approximation of the true of like the true solution. You know what I mean? Like these numerical methods, they're all approximations of some true like underlying symbolic solution that you could like theoretically come up with. But yes, we get smaller and smaller delta t, we get like more and more precise solutions here. So let's just try one more. Let's just try delta t equals 0.01. And yeah, so here we get even more precise of a solution. So here it looks like our Euler's method solutions like very, very closely match the actual SciPy method, although still not exactly. There's still a little bit of a difference, But yes, as we use smaller and smaller delta t's, we get closer and closer and like more precise approximations of the true solution, basically. But yes, that's Euler's method in Python for the Predator-Prey model. Hope you guys understood everything okay. If there's any questions, just let me know in the comments and I'll try to answer them. Also, like usual, I'm going to be posting the code on my GitHub if you guys want to download and try it yourself. I'll put a link to that in the description. But yeah, thanks for watching and see you guys next time.